Now, what was the next problem? The one we were going to do? With depth. D. So now we are going inside the earth. Imagine I am going to take some very bold assumptions that the mass of the earth is ME and it has uniform density. That is very bold. And I'm going to call this E, and I'm going to say that the radius is RE. Very, very bold assumption. And it's all a sphere. So first we were doing outside. At a height 8, x. Now we are going to go inside the earth. So with this very bold assumption, may I write rho of E as mass of E over V of E? That doesn't look good. So what's the volume of a sphere? 4/3. Thank you. So can I then write the mass of the earth as 4/3 pi r e cubed rho of E? Did I write my value of G as GME over RE squared at the surface? May I plug this in here? Will I get G 4/3 pi RE rho E at the surface? May I call this equation 3? Then at depth D, will my GD become G 4/3 pi radius of the earth minus D rho E? May I call this 4? Okay. May I divide equations 4 and 3? GD over G equals 4/3 pi RE minus D rho E divided by G 4/3 pi RE rho E. Nothing fancy so far? G's get canceled, 4/3 get canceled, pi's get canceled, rho E gets canceled. Am I left with RE minus D over RE? Okay, may I rewrite this as 1 minus D over RE? And then may I rewrite this as GD equals G minus D over RE G? What does that equation say to you? This is the gravity at depth D, acceleration due to gravity at depth D. This is the acceleration due to gravity at the surface. The minus sign indicates what? GD is being reduced by that factor, right? So here's what the magic happens. What happens when D equals RE? When you're actually at the center of the earth. What does the equation tell you? You get 0. You are weightless at the center. You ever reach the center?
With a lot of pretty lenient.
Yeah, I mean, there's big assumptions that we've made, right? Of course, Earth is not a uniform sphere. Of course, the density is not constant. It's just fun to do this exercise.